Hello there, it's Ed from M&E Pins, and I'm down here at Mike's shop to test out a new capability we are working on. So let me turn the camera around and give you a little peek. We have been working for a while on trying to get our rollovers to be non-mechanical. And we have found these inductive sensors. So in the last video I did, I showed you how we were milling out the old rollovers and replacing them with new clear rollovers. And this is just a continuation of that effort where we mount an inductive sensor into that rollover. So I am working on the electronics to interface that sensor to the pinball machine. And that electronics is right here. It is simply an optic isolator and a dropping resistor to drop it. Now in the final product we're going to build a board that has LEDs and all of this built onto one board and will also help hold the sensor. But right now I have the output from that optic isolator just wired across the normal rollover switch. So if I go to the rollover switch and just push it on the other side, because it's still hooked up, you can hear that it's giving us credits for whatever we're doing. Now down here, if I bring the ball with, this is a 4mm sensor, so if I bring the ball within 4mm of this sensor, it registers, and it's quite sensitive and quite fast. These sensors are relatively inexpensive, costing between $2 and $4 depending on where you get them from. They are the same sensors used on 3D printers to sense the bed leveling. Well, it's a variety of that. So anyway, it works really great, and no moving parts. It's awesome. I'll show you the board we're building to go along with this, and we'll get those ordered, and I'll show you what it looks like when it's in a machine working. Before we go into the board that I'm designing and building, I want to tell you a little bit more about the sensors we're using. So here is an ad from Amazon. It's 2 sensors for 12 bucks, so $6 a piece. The sensors we're using are NPN normally opened sensors. What that means, the NPN means that this sensor is going to switch a ground connection on and off, and the normally open means that the sensor is not conducting unless it senses something, and then it closes and current flows. We're using 12mm pitch on the screws, on the threads, and it's a 12-1 if you're wanting to do anything with that. And it's a 4mm sense area. Now the farther away you want to sense, the bigger the barrel of the sensor gets, because it has a magnetic coil in the end of the sensor, and that coil has to get bigger in order for the magnetic field to reach out farther. Notice that this thing runs on 6 to 36 volts. So the normal 5-volt system of a Bally is not in the range of this sensor, so you have to build some kind of interface. And that can be really simple, or it can be more complex. We opted for the slightly more complex way. But we are powering this off of 24 volts DC. It's the same voltage we're using to drive our backlight lights. And because we have the 24 volts available, it's a nice strong voltage to drive these sensors. I looked up the specs of the sensors, and they only draw about 15 milliamps. So even on a play field with a half a dozen sensors, you're only going to be pulling about an amp max off of that 24 volt bus. So anyway, those are the sensors. one thing about the sensors, let me see if I can find, yeah, this one doesn't really show. This picture shows it pretty good. There are 3 wires. All the sensors, and there's millions of these sensors out there. They're all wired with the same color code, blue, brown, and black. Now, in our world, black would normally be ground. Well, it's not here. Blue is ground, black is the output signal, and brown is the input voltage, which in our case is 24 volts. It's a little weird, and I wired it wrong when I first hooked it up, and it didn't work for some reason. But, we figured it out. So, anyway, so that's the sensor we're using. Now, just for comparison, here's an AliExpress ad for the same sensor, and it is only 80 cents from AliExpress. Now, unfortunately, AliExpress being in China, there's a $2.36 delivery fee for that one sensor. So that still drives it up to about $3 and something. The best price I've found so far, and you can look all around and find them, but I can get like 30 of them for about $66. So just a hair over $2 a piece for them. There's probably better prices out there if I looked around, but $2 a piece for the sensors isn't bad. So those are the sensors. Now let me show you the board that we're going to be using. So here's the schematic. There's a 24 volt input connector, I'll call it. They're just pads on the back side of the board, and I'll show them to you in a minute. But so there's some 24 volt pads. There's 4 of our programmable LEDs. These are RGB LEDs that we can program, so we can change them. And it has an input pad and an output pad to bring that signal in and out of the board. One thing important to note on my board is the ground on here is the only ground for this board. I didn't bring ground in separately for the 24 volt line because all the grounds are common in our configuration of pinball machines, so I didn't need to run 2 different ground wires to the same little board. And then here is the, if you will, the magic of the design, and that is an optic isolator. I use a couple of resistors, 24 volts dropped across this, trying to pull about 10 amps, or 10 milliamps to turn this optic isolator on. We'll drop about a quarter of a watt of power across here. So just to make sure that I'm safe, I have 2 quarter-watt resistors in series. Give me a half a watt of dissipation. I know that's overkill because this thing only comes on and off for just a second once in a while, and I'm sure one resistor would have handled it, but I don't like things to burn up, so I'm playing it safe. And the output simply goes to a couple of pads which connect to the switch array, and the switch array labels their signals as inputs and strobes. So pin 1 goes to the strobe side, and pin 2 goes to the input side. So that's what the logic looks like. Here is a rendering of the board that we're going to be building, and we have all of our boards built at JLC PCB. They're on holiday right now until the 3rd, so as soon as they come back to work, I'll place an order for this board, and hopefully I'll get it in a week or 2, and then we can put this thing together and try it out. But you can see that there's 4 LEDs evenly spaced on the board. Here's the optic isolator. Here's a couple of dropping resistors. I did place capacitors in the schematic. Some of these 2812 LEDs require capacitors, some don't. So depending on which version goes on the board, that capacitor will either be populated or not. And on the back side of the board, you can see the connector. This is where the sensor will plug in. The sensor will go through this hole, and it'll have a short lead coming out of it, which will plug in here, and that will give the the sensor 24 volts and ground and bring back the signal from that sensor, which we take out to the optic isolator on the other side, and that drives our output to the Bally switches. So let me turn this up a little bit more. You can see the blue, black, brown. Brown is the 24 volt line, black is the signal line, and blue is the ground line. So we have 24 volts coming into the board, and this is just daisy chain. These two connectors are hooked together. So if you have another board, you'll bring your 24 volt line in here and it'll exit right here. And then this is the switch output, the strobe line, and the input line. And because the optic isolator over here has a transistor output, you don't need that series diode that's in the switch matrix. If you've ever looked at the switch matrix of any pinball machine, in it, every switch, almost every switch, has a series diode in it to keep current from flowing backwards when there's more than one switch active at one time. That's not necessary with this because the solid state components inside the optic isolator will handle that for you. And that's pretty much all of the board. The only other thing you might have noticed these holes in here, and that is for installing a little 3D printed plastic nut to screw the sensor into, and that looks like that. So this will be printed. I haven't picked the filament yet, but probably polycarbonate or something like that. And I've already printed several of these, and it works great. The sensor screws in, holds tightly. It's a firm thing. So this will be stuck in to the board from the bottom. So from this side, the nut will be sticking out on this side, and on the other side, those two pegs will come through these two holes, and we'll just use a soldering iron to melt them down, heat stake them down basically, and that'll hold the sensor together. I'll probably put a few drops of glue on there also. The heat stake will hold it together until the glue cures, and then we're done. And since this sensor is replacing the mechanical rollover switch, this part of the board will sit where that mechanical switch sits today. So it's just as wide as the hole. It's just a little bit over 1 inch wide, about 1 3/4 inches long. Tiny little board actually. So anyway, when I finally get the boards ordered and get them built up and tested and installed, we'll show them to you. So that's going to do it for this video right now. Thanks for watching, and I hope this interests you.